Sound as a wave. Sound is created by vibrating objects. A tuning fork is an example of an object that can be vibrated to produce sound waves. As it vibrates, the prongs, these things here, create disturbances in the air which move it out in all directions. These disturbances push and pull the air molecules into each other as the tuning fork moves one way and then the other. A piece of chalk was attached to the vibrating tuning fork, so not sure how you'd exactly do it, but let's pretend it was attached right there. There's your chalk. Okay, and then it wrote on a rotating cylinder. So here's our cylinder. I'll make it a little longer, and that's rotating around. The chalk pattern looked like this. It would go up, come down, and just kind of follow that path. What conclusion can you make about the tuning fork? What's it producing? The tuning fork, the vibration of the tuning fork produced waves. And since the tuning fork also made a sound, we're going to call them sound waves. And you can click here to see a nice video on sound waves. The tuning fork produces a very clear sound that has a constant frequency. And if you have a tuning fork, well, even if you don't, you can look over there. It actually shows the frequency and what letter it is in the musical scale, like A, B, C, whatever. So, what if the size of the tuning fork changes, but it's still made of the same material? Please watch this video and state whether tuning fork A or tuning fork B has a higher frequency. Tuning fork B has a higher frequency because it has a shorter length than tuning fork A. The massive pipe organ, and here it is. All those vertical things are pipes that air flows through and makes nice sounds. The pipes perform the same function as a tuning fork. The larger pipes produce lower frequency sounds, also called lower pitch. What is pitch? Pitch is a description of how you hear a sound. An eagle screeching is a high-pitched sound. It has a high frequency. Higher frequency sounds have a higher pitch. The rumble of truck tires on the road is a low-pitched sound. It has a low frequency. Lower frequency sounds have a lower pitch. The wave shown on this slide has a lower frequency than the one shown on the last slide, so it would also have a lower pitch. Higher frequency sounds are heard as higher pitches by people and animals, right? Dog whistles are a very high-pitched sound that humans can't hear. Lower frequency sounds are heard as lower pitches. And there's a relationship between intensity and frequency and how you hear sounds. And click on this video for more information. Last chapter we talked about the amplitude of waves. Now amplitude is heard by the human ear as loudness. We have a graph here, the waveform of a sound. Way more complex than just the waves we were drawing last chapter. The graph is a waveform of a sound. The amplitude of the wave varies from beginning to end. Can you tell where the sound is loudest and where it's softest? The loudness of a sound is measurable. It also depends on how far you are from the sound source. A loud sound might not be heard very well if you're very far away. But for this graph, let's assume you're at the same place where the recording equipment took the data. In that case, over here, where the amplitude is the largest, that's where the sound is loudest, and that you'll hear it the loudest. Down here somewhere, it's the softest. And another video. Click here to see a video on sound loudness and the decibel, which is how you measure sound loudness. That's the unit we're going to use. We use intensity, right over here, to quantify the loudness of a sound according to the distance from the source. Because there are a wide range of intensities that people can hear, the decibel scale is used. It's a logarithmic scale. Not sure if you had that in math yet, but you will. And you can see what the problem is. You can hear all the way down to 1 × 10 to the -12th watts per meter squared. Watts is a measurement of power. You can also hear all the way up to 100. That's what, 14 orders of magnitude. That would be crazy to kind of figure out what's going on there. If you can say, hey, I can hear something at 1 × 10 to the -8th, and I can also hear something at 100. That's because the ear hears logarithmically. So the threshold of hearing is down here. You can just barely hear that sound, but you can also hear this sound. And frankly, since you're over 135, it's going to hurt your ear a bit. So a jet plane at 30 meters sounds very much like the threshold of pain. Even though the intensity is 100 times that, it sounds almost same to you. So this is what they're going to use for sound levels, decibels, both from a mathematic point of view and also biological point of view, because that's how your ear hears. In open areas, the intensity of sound decreases with distance. The closer you get to the source of the sound, the more intense the sound, and therefore the louder it is.